All right, guys, happy Tuesday. I hope everybody's doing well. At this time, if you have not already done so, the corrections and your tests from the Chapter 15 test need to be turned in at this time. And hopefully you did those and we'll get some additional points. We talked about a lot of information yesterday, so I wanted to start this class with an example problem that we can look at to make sure you had a good understanding. When I return, we'll look at the homework from the chapter review to make sure everybody has a good understanding of this, because this is probably, it's not that it's hard application, but out of all the application in this chapter, it does take a little bit of thinking, and you got to be careful with a couple of different pieces. So I wanted to start with one that was a little bit different in one aspect, and I think you'll see what I'm talking about as soon as we look at it. The problem says a sulfuric acid solution has a hydronium ion concentration of 3.2 times 10 to the negative second moles per liter. So that's its molarity, and that's great. Now, if you guys can recall, when we were doing all those conversions yesterday, most of the ones we looked at were 1 times 10 to something. Well, this one's different because it's 3.2. And when it's 1.0 times 10 to something, you can take the exponent and move it in, move it to pH, and then go from there. But this one's a little bit different because you start with 3.2. So the very first thing we have to do in order to calculate the pH, the pOH, and the hydroxide concentration is we got to figure out the pH first. Because it is not, the concentration is not 1.0 or just 1 times 10 to a power, we first have to use that formula, the log formula, to calculate what this is actually going to be. So the pH, if you guys remember, is equal to the negative log of the hydronium ion. This problem gave us the hydronium ion value. That was the molar concentration. So I just plugged that in. You use your calculator, so get your calculators out if you don't have them out already. And I'll give you a second or two to get that out. You got to remember this formula. This is very, very important, okay? So please make sure you remember this formula. This formula will work if it is 1 times 10 to a power, okay? It's just there is that little shortcut if it is 1 times 10 to the power. But we've got to use the formula because it's not. It's 3.2 times 10 to a power. So you hit on your calculator, hit log, hit 3.2, EE, and then hit the negative sign, not the subtraction, but the negative sign too. Hit equals. You're going to get a negative value. You're going to get negative 1.50. If you do not get negative 1.50, you're obviously doing something wrong, but it may not be you. It could be your calculator. You got to make sure your calculator is in degree mode, okay? Most of the calculators will have a letter, the letter D, in either the top right or top left, or sometimes it's in the bottom right or bottom left corner. You won't see that D because that means you're in the decimal system, and not R, which is not decimal. That's wrong. It's the degree symbol, degree system, not R or G for radians or gradients. So make sure you're in degree mode, okay? But you get negative 1.50. The negative times the negative is a positive, so you get a pH of 1.50. So your hydronium concentration was 3.2 times 10 to the negative second. The pH is 1.50. Now what I'm going to do is I'm going to go straight from pH to pOH because I can go directly there. If you guys recall from yesterday, pH plus pOH is equal to 14. So I had that value. Here it just solves for pOH. It's 14 minus the pH. I like to ask the question, what plus 1.5 is 14, but you can set it up this way. You just subtract 1.50 from 14 and you get 12.5. So the pOH is 12.5. Since you know that is correct, you can calculate the hydroxide ion. The hydroxide ion concentration can now be calculated from the pOH. And this is where a new formula is. We didn't talk about this yesterday. It was in the flow chart. To calculate the hydroxide ion, it's 10 to the negative pOH. So you can do this one or two ways. If you find your log button, usually right above the log button, it'll say 10 to the X. Okay, you can hit that shift or second log. It'll display 10 to the X, and then you hit your negatives button, and then you type in the POH. You can do that, or you could use your power buttons. You could say 10 raised to your exponent. So sometimes it looks like a upward arrow that is called a caret. Sometimes it'll say X, Y to the X or something like that. So depending on how you feel comfortable, you can use two different methods to calculate this, okay? So I go, the hydroxide ion is 10 to the negative POH. So that would be 10 to the negative 12.50. Again, you can hit 10 and then hit your exponent button, or should be able to hit shift log or second log, and it should display a 10 to the X. Look for that button at least, and that's how you plug that in. Plug it in and you get 3.2 times 10 to the negative 13th power. Again, we couldn't use that little trick because you remember the trick we used before. We went 12.50 and said 1 times 10 to the negative 12.50. We can't do that because we didn't start with a 1 times 10 to the certain power. I always recommend to use this formula here because you're never going to go wrong. So it's either 10 to the negative POH. Remember, POH goes with hydroxide. If this said 10 to the negative pH, you would have H3O positive, okay? So that's one way to do this particular problem. Okay, acid and bases strength. This is a new concept. Good part about this section, the final section, section B, is that it's not very complicated in terms of there's no application. So that's probably a good thing for most of you. Probably prefer that until we get to one element, and it's not too difficult. All right, strong acids lose their hydrogen ions easily and completely. So if it's a strong acid, it will lose the hydrogen ion quickly and easily and completely. Now that's what actually determines if something is an acid, a strong acid. It's how fast and how easily and completely it releases or loses that hydrogen ion. So if you have an acid, if I just give you a generic acid and I say this acid loses its hydrogen ion easily and completely, then you know that's a strong acid. An example of this would be hydrochloric acid. If you look on page 408, so go ahead and open your ebooks to 408, there is a chart here. You need to know a couple of these on this chart. Okay, I'm not going to test you over all the components to this. I will require you, though, to know your strong acids. And if you look in the textbook on 408, that chart there, the first several few are bold. The perchloric acid, hydriodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid. Know all of those, okay? Those are all of the strong acids. So you got to know those ones that are bold there in that chart. Strong bases, on the other hand, they lose hydroxide ions easily and completely. So strong acids lose the hydrogen ion. Strong bases lose the hydroxide ion easily and completely. That is the technical definition of a strong acid and a strong base. You got to know that, okay? Example of this would be sodium hydroxide. All right, you see there are some strong bases on that chart as well. Look back on 408. Look at the far right column where it says base. Go all the way down to the bottom and you'll see the ones you must know. Hydroxide ions, amide ions, hydride ions, and methide ions. Those are the strong bases that I want you guys to be familiar with on this chart. Okay, so know your strong acids and your strong bases. Okay. All right, let's move right along. Weak acids and bases do not ionize completely. Okay, so that's the definition of a weak acid or base. It doesn't ionize completely. In other words, it doesn't lose all of its ion. It still has some remaining. Okay, so that's the definition. Hydrogen bromate is an example of this. And then calcium hydroxide is a base. Just different examples there, okay? So please make sure you know the definitions of a strong acid and strong base. It all has to do with how much they ionize. Concentrations versus strength. A strong acid can be concentrated or diluted, okay? Now this is important because some students get this confused all the time. The power of the acid has nothing to do with how much acid is in the solution. A 10 molar solution of hydrochloric acid, that's almost pure hydrochloric acid. 12 molar is pure hydrochloric acid, okay? So 10 is very close to that. But notice the 0.05 molarity, that's a lot less strong in essence of a concentration. Now but remember, that's not what we're talking about here. We're talking about a strong acid. The concentration is greater here than it is in the 0.05, but the acid is just as strong. Okay, so please do not get concentration and strength confused. Concentration is how many moles per liter there are. There are 10 moles of hydrochloric acid per every liter here. There is 0.05 moles of hydrochloric acid for every liter here. So they're diluted. The concentration is different, but the strength is the same. Okay, this 10 molar concentration is going to release its ions just as fast as the 0.05. It's going to do it the same speed. Theoretically, it's going to do it at the same speed. But the strength and the concentration, those two terms are not synonyms, so make sure you do not assume that they are. Okay, concentration deals with the molarity, how many moles per liter. Strength deals with the actual chemical makeup of the compound, or the molecule in this case, the hydrochloric acid. So again, please don't get that confused. The same is true for strong bases and for weak acids and bases. It's the same thing. The concentration does not have an impact on the strength, because remember, the strength of an acid or a base is how fast and readily it releases its ion. It has nothing to do with the moles per liter. So please don't make that mistake. That sounds like a good true and false question to me. All right, the stronger the acid, the higher the acid ionization constant. So here we go. This is a new term here, an ionization constant, K sub A for acid. And then you could probably guess what the base ionization constant is. It would be K sub B. The stronger the base, the higher the base ionization constant, K sub B. All right, so you'll need to know that if it's a high number, a big number. If I give you two acids and I say one K sub A for acid number 1 is 12, K sub A for acid number 2 is 3, then acid number 1 would be the stronger acid. Okay, so that's how that works. Same thing with base, same exact thing. If I tell you that the base is 14 versus the base that is 3, the one that is 14 is higher, so it's the stronger base. All right, here's a generic formula that you do need to know. The acid ionization constant, K sub A, times the base ionization constant, K sub B, is equal to K sub W. And we all know what K sub W is. That's the ionization constant of water. So that's another place that this comes into play. All right, true or false? All concentrated acids are strong. Concentrated means it's the molarity is very high. It's like concentrated orange juice. You take that concentrated orange juice and put it in water to make the orange juice you drink in the morning. So all concentrated acids are strong. True or false? That would be false, because remember, concentration and acid are not the same thing. All right. Conjugates and strengths. Conjugates and strengths. This is a pretty interesting little section here. But before we do, there is one statement on page 408 that I want you to know. It's on the only paragraph at the very bottom of the page. It talks about the strongest acids are more polar and the lower bond and have lower bond energies, and that's probably an easy understanding of why a strong acid or base would be more polar, because it has that extra region of electrons that can be bonded. And you can see some examples on 409, but you really just need to know that statement. strong acids are polar, basically, is what you need to be familiar with. Okay, so conjugates and strengths. Conjugates and strengths. All right, we're going to have a couple terms here, and then we're going to figure all this stuff out. If an acid is weak, its conjugate base must be strong. So this is very important. Remember we talked about conjugate pairs when we talked about the Bunsen-Lowry acids. And we talked about a Bunsen-Lowry acid is the one that donates the proton, or basically whichever one has more of the hydrogen is the easiest way to figure that out. So if an acid is weak, its conjugate base must be strong. So if you figure out that the acid is weak, then you know its conjugate base is strong, and vice versa. Whatever is true for the acid, the opposite must be true for the conjugate base. So if the acid is strong, then the conjugate base would be weak. If the conjugate base is weak, then the acid would be strong. Conjugate acid would be strong. So it's just pretty basic here, but it should make a little bit of sense. And we're going to actually figure out some of this in a second. If one reaction is favorable, meaning it's going to happen or it's going to be downhill energy-wise, the opposite reaction must be unfavorable. So that's just equilibrium there when it comes to the conjugate strengths. If one reaction is favorable, the opposite reaction must be unfavorable. So causes of acid strengths. The cause is electrical in nature. Its strength, and it goes back to what we just talked about polarity. The location of arrangement determines how easily protons can be accepted or given. Again, this goes back to that statement I just gave you about strong acids are polar in nature because they're going to want to bond to something because they have that unbonded pair of electrons, or there's a region there that can be bonded to. So the cause is electrical. It's because of the electrical charges, the electrons, and the location and the arrangement of the electrons determines how easily protons can be accepted. Again, that should make sense going back to the Lewis dot structure in your different shapes of your molecules, tetrahedral, trigonal planar, that kind of stuff. Okay, amphoteric substances here. Amphoteric substances, this is on page 410. This isn't too bad. I think you're going to be just fine with this. Bless me, bless me. Amphoteric substances. A substance that can be either an acid or a base depending on its condition is the technical definition of an amphoteric substance. Water is a good example of this. So if you put water with an acid, then the water would have to be the base. If you put water with a base, then the water would act as an acid because remember, you have the two ions. It could be the hydroxide or the hydronium ion, the positive or the negative, which is going to have an impact on it. So this kind of goes with conjugate bases and conjugate pairs as well, conjugate acids and bases. If again, the amphoteric substance that can be either an acid or a base depending on its condition. Really what it's bonded to. It acts the opposite of the substance to which it is exposed. So if water again is exposed to an acid, the water will act as a base. If water is added to a base, then water will act as an acid, all right, because it is an amphoteric substance. Okay, polyprotic acids. This is actually pretty simple here, but I think you'll understand this, and this is very important for a couple of things that we're going to be talking about down the road, potentially. A couple terms here. Polyprotic acids, you have something called monoprotic. Monoprotic can give one hydrogen ion. Now this is very simple because if you look here, hydrochloric acid, it only has one hydrogen to give. So that's why it would be considered monoprotic because it could only give one hydrogen. Here, H2CO4, this is called diprotic. Diprotic because it can give two hydrogens. There are two hydrogens there to give, so it's called diprotic because it can give two. Triprotic can give three because here, hydrogen phosphate, here you have three hydrogens to give. So when you mix the hydrogen phosphate in something else, like water, it can donate up to 3 hydrogen ions. So that's what it's considered polyprotic. Both diprotic and triprotic are called polyprotic because they have more than one. So really you need to know poly, and you do need to know di and tri, but you also want to remember that diprotic and triprotic are called polyprotic. Polyprotic acids have smaller K sub A's, so the ionization acid constant, they lose successive protons. So if they're polyprotic, they typically will have a smaller K sub A. They become more negatively charged, thus it becomes harder to lose more positive protons. Because they're going to want to, if you think about it, and again, it's a little bit more on the abstract stuff, go back to your mindset of the atom itself. You had the nucleus where the protons are located. I guess I can draw this out here if it'll show up. Here you have the nucleus here, that's going to represent the first energy level. And then you had all these nucleus. In the nucleus, you have your neutrons and you have your protons, okay? I know it's a really terrible picture, but it'll help you understand what we're talking about here. Polyprotic acids become negatively charged because it's going to be, when they become negatively charged, it's going to be harder to lose positive protons, because if there are more negatives around here than positives inside, basically, because it gains an electron, they're going to be very closely attracted to this. But remember, if there's a negative out here somewhere, the negative is going to be repelled because there's that force going this way, and this one's force is going this way, but there are more pushing out. Since there are more pushing out, it's going to be very difficult for that one to basically bond to those positive charges. So I know it's a little rough of a picture, but it helps you understand kind of what this is talking about. Polyprotic acids, they become more negatively charged, thus it becomes harder for them to lose more of their positive protons. Okay, question. HNO3 is triprotic. HNO3 is triprotic. That would be false. This would be monoprotic, because how many hydrogens do you have here? You have one. So it's not triprotic, it would be monoprotic. Okay, moving right along here, we're going to have to go back in a second to talk about some pieces. Let's do that before we go. Everybody look on the bottom, page 410. You can see what I'm talking about when we're talking about calculating or showing the differences in the diprotic and polyprotic. It goes through and it calculates all this stuff for you. It shows the equilibriums here. If you look, and again, I'm right in the example or the actual work part of 16.12. So find 16.12 on page 410, and I'll explain this to you. You have the first equilibrium, the H2CO3 plus H2O, equilibrium HCO3 plus H3O. So what they calculate the ionization acid constant, and you can see what they did. It's what we've done before with rate loss. So they put all that information in. Notice water's taken out. The water, H2O, is a reactant, but it's taken out because it's a liquid. So they actually calculate that. Those numbers that they have there would be derived from the chart that we looked at, that I said you guys had to memorize the strong acids and the strong bases. That tells you what the actual constants are. So you find that one, and then you look in the second equilibrium. It donated 2, so that's where you get the K sub A1 and the K sub A2. So whenever something is polyprotic, meaning again it has 2 hydrogens or 3 hydrogens to donate, something very important is stated on the next page that you got to know on page 411. It's right above the term triprotic. So make sure you underline this. The Ka sub 1, the acid constant, is greater than the Ka sub 2, is greater than the Ka sub 3. That's something you got to remember, you got to memorize. So the first energy is greater than the second and the third. This should make sense because remember, K sub A of 1 means it donated 1 hydrogen. So the acid that is remaining, the H2 in this case, would be very strong. But then the H2 donates another electron, or another hydrogen ion, I should say. So it would be H3. I'm sorry, so it would be H. So you go from H3 to H2 to H1. So the lower you go, the less electrons you have involved there. So that's why they come up with that. So you do need to know that little simple statement. K sub A of 1 is greater than the value of K sub A2 is greater than the value of K sub A3. Kind of helps you see that. All right, let's finish this out talking about something pretty simple here, indicators. Indicators change color when pH changes. So this is what I was talking about with pH paper. You dip a piece of pH paper in a solution. Based on what color it turns, it's going to tell you what the pH level is. It's just a rough estimator. It doesn't give you an exact answer because it's a color, and colors are going to be different, tinted differently. It's not as exact as a pH meter. pH meter, it's a device you put into the solution, and it reads exactly what the pH is. All right, so let's talk about this. A couple of universal indicators. A universal indicator is a combination of indicators used to show a wide range of color changes over the 0 to the 14 pH scale. Transition intervals, a range of pH value over which a color change occurs. So certain indicators are only certain colors. They'll tell you if it's an acid or a base, like litmus paper. It turns blue for an acid. It turns blue for a base and red for an acid. It doesn't change the shade of blue. It's not like Carolina blue is slightly basic and Duke blue is very basic. It doesn't do that. It's just blue or red. So it's more of a transition interval. There are lots of different ones. Phenolphthalein is one that's commonly used. Bromethyl blue is one that's commonly used. Lots of different ones are used in order to figure out different pieces. But you can actually use fruit and different other indicators, natural indicators as well. So here's an example. I was talking about some of these. Methyl violet will only give you the range of 0 to 2. So if it's something over here, depending on what is used, it may not even show up. But usually what it means, if it's like a purple, it's greater than 2. Here you have bromethyl blue. That's one I was talking about that's commonly used. Litmus, there's litmus. Kind of shows you the phase there. Thymol blue is used too. If it's yellow, it's going to be usually less than 8.5. It goes back this way. These are just ranges of indicators. So these would be the transitional, again, the transitional intervals here, what we're talking about. Just the term. Here's some cool ones though. A lot of people use this for science projects. They'll take fruit or vegetables and test pH. You could take a red apple skin and you basically have to blend it up and make it a liquid, and you put that liquid inside of the solution and it will turn one of these colors, and based on the color it turns will determine what it's used. Science project that a lot of people use are the red cabbage. You put red cabbage in a blender, and it kind of will change that color based on what pH it's in. It does have, if it's yellow, it's going to be above 12 of a pH. So just an interesting little aspect of indicators. More indicators here listed that can be used in order to determine a liquid's pH. So that's pretty much it for today, guys. It's not too bad of concepts today, but it is important to be able to figure that out. What I want you guys to do tonight for homework is on page 413, you see section review 16B. I want you guys to complete that. That'll give you some more practice with the pH scale, like converting from hydronium to pH and stuff like that. And it also has a couple of other application problems that you'll need to be able to do. So again, tonight's homework is to complete section review 16B. Have a great day.